A buffer is a solution of a weak acid and its conjugate base. It is useful for reducing changes in the hydrogen ion concentration of a solution when additional hydrogen ions are removed or added. And so that means that it resists changes in pH. So now, say if you were to take a look at this reaction right here. So I talked about a weak acid and its conjugate base. So we have this weak acid and its conjugate base. And so you see here, this weak acid dissociates in this reaction. Now, this reaction is at equilibrium because it has a double-headed arrow, meaning this reaction is moving in both directions. So not only is this weak acid dissociating into its principal parts, but the parts over here are forming back together to form that weak acid. And so say, for example, that some of this right here was added. What's going to happen is the reaction is going to shift to the left, and more of this weak acid is going to be produced. Now, say, for example, if this was added, it would combine with this right here, and so it would reduce the overall level of this, and so it would shift the reaction to the right. And so notice here that the buffer solution reduces the changes, and this right here that might occur otherwise. And so some examples of buffer systems include an acetic acid with sodium acetate, and another one is citric acid along with sodium citrate. And so again, a buffer is a solution of a weak acid and its conjugate base that resists changes in pH. Catalysts are substances that speed up the rate of a chemical reaction without being consumed in the process. And so the way a catalyst works is first by lowering activation energy. And it lowers the activation energy that is required for a chemical reaction to proceed. And so by lowering that activation energy, the chemical reaction can proceed more easily. Now, another way that a catalyst meets its objective is by providing a surface for molecules to come together and to bind. And so to provide a surface for molecules to come together, to bind, is faster than just random collisions of reactant molecules. So that is how a catalyst meets its goal of speeding up the rate of a chemical reaction. Now, we can classify catalysts as homogeneous catalyst and heterogeneous catalyst. So a homogeneous catalyst is in the same phase as the reactants. So say you have a liquid reactant and you have a liquid catalyst, then it's a homogeneous catalyst. Now, a heterogeneous catalyst is just the opposite of that. The catalyst is in a different phase than the reactants are. So some examples of this would be, take liquid bromine, for example, and it speeds up the breakdown of liquid hydrogen peroxide into liquid water and oxygen gas. So you have liquid bromine and you have liquid hydrogen peroxide. So those are in the same phase, so that's a homogeneous catalyst. Now, take, for example, the combination of ethylene and hydrogen gases to make ethane gas. It's catalyzed by adding powdered nickel. So you have powdered nickel, which is in solid form, and everything else is in gas form, or the gas phase. So in that reaction, nickel is a heterogeneous catalyst. So an important point to remember is that catalysts are substances that speed up the rate of a chemical reaction without being consumed in the process.
Today we want to go over just some of the basics of chemical reactions. We don't have time today to do this thoroughly or fully in depth, but just want to go over some of the basics of chemical reactions. So when we think about chemical reactions, one of the things we ought to think about is time scale. How rapidly or slowly do chemical reactions take place? And in terms of time scale, obviously we're measuring this from our vantage point, from our viewpoint, so on the human time scale, the way we experience time. Chemical reactions can happen very rapidly, very quickly, and also very slowly. From the lower end, just fractions of a second for a chemical reaction to take place, all the way up to the upper end, years and years and years and years and years before a chemical reaction fully takes place. And everything in between. So with chemical reactions, the time scale is from fractions of a second all the way up to lots of years for them to take place and everything in between. When we think about time scale, we also think reaction rates. What affects reaction rates? So in a chemical reaction, we need to think in terms of the frequency of the contact between the chemical components that are reacting. If it is very little contact, you have a slower rate. If they don't come into contact very often, that also slows it. If there's a great mixing of these things that react volatilely, you can have a very rapid reaction. So it's the frequency of contact between the interacting chemicals. The temperature plays a role. Higher temperature, lower temperature can affect not only the reaction but the time rate as well. And then the properties of the chemical that is interacting. Is it a solid, a liquid, or a gas? The shape it's in. All of these things play a part in reaction rates. Frequency, temperature, and properties. Then when we think about reaction rates, you can actually influence those rates. You can accelerate a reaction rate. This is called using a catalyst. A catalyst is introduced into that chemical reaction which greatly speeds it up. And that's the catalyst's only job, is to come into this interaction between these chemicals and to speed up that reaction that would ordinarily take place over a slower period of time. You rapidly increase it. But you can also decrease reaction rates, and this is called using inhibitors. If you introduce an inhibitor into a chemical reaction, it slows it down. It keeps them from reacting as quickly. So you can affect reaction rates not only naturally and through ways that you're able to control temperature and what form it's in, things like this, but you can also introduce other chemicals, catalysts to accelerate and inhibitors to decelerate the reaction times of the chemical reaction. Now, chemical reactions can, when they occur, release heat, release light, electrons, ions. There's usually some form of product from this interaction, this chemical reaction that's taken place. Sometimes chemical reactions send the temperature in the opposite direction, but usually it's things like heat and light, electrons being traded or spun off, ions, radicals going off, things like this. And then finally, heat and other factors can influence chemical reactions and help break bonds. If you think in terms of breaking down carbon bonds, this is done obviously in the production of oil and related materials. You've got strong, stable carbon bonds that need to be broken down and split up. Heat is usually a thing that is primarily used to help break those bonds, divide those things up, and then sort them out to their various functions and purposes. And if you ever do any sort of research or study, it's very fascinating to look at an oil or a chemical plant and how they bring in the raw materials using heat and other pressure and things like this to break up the raw material that's brought in into various other materials, sift it out and sent other places and put to other uses. It's fascinating. But anyway, chemical reactions then, just the basic overview again, time scale from fractions of a second to years and years and years. Reaction rates are affected by the frequency of contact, the temperature at the point of their mixing and their contact, and then the properties, solid, liquid, gas, the shape of it, these sorts of things. Reaction rates can be accelerated with catalysts, decreased with inhibitors. Chemical reactions produce things often like heat, light, spinning off electrons, ions, things like this, and heat and other factors influence chemical reactions and help to break bonds. Once again, this has just been the basic overview of chemical reactions. If you'd like to learn more about this or related matters, underneath this video you'll find a link. If you'll click on that link, it'll take you to the website that has that information, and while you're at that website, you'll also find a link to an ebook that's ready for immediate download. Today we're going to go over combustion and terms and concepts related to it. So if you look at the board behind me, we'll just start at the top here. When we talk about auto-ignition temperature, when we think about auto-ignition temperature, we're talking about the temperature at which a substance is so hot that it just bursts into flame without need for an ignition source. As things get hotter and hotter, most substances, though not necessarily all, have a point at which when they reach that temperature they will, if there is oxygen or other medium in which it can burn, burst into flame on its own without the need for an external source of combustion, heat, fire, anything like that. It just on its own, spontaneously. And so it would be tied into number 5 here, spontaneous combustion, no source of ignition. When we think about things that don't need a source of ignition and yet burst into flame, we can think in terms of maybe a compost pile. As the compost pile sits there, it's got hay and other things in it probably. It's strongly insulated, and there's fermentation going on inside of it through the bacteria, which is generating heat. And as the heat rises because of the insulation, there's nowhere for it to go. It eventually reaches a temperature at which ignition can take place without an outside source, and it bursts into flames. And so sometimes people do have compost piles that go up in flames because of the spontaneous combustion medium, the fermentation by the bacteria, raising the temperature, it's well insulated, and then boom, up it goes. When we think about combustion, we have certain types of reactions. Exothermic reactions are those that give off heat. They generate heat and force it out, sometimes light, sometimes noise in the form of explosions, but exothermics give off. Endothermic absorb or take in heat in these kind of reactions. So there is a heat transfer taking place here. Exothermic forcing it out, endothermic pulling it in, absorbing heat inward. When we think of endothermic reactions here, you can think of these sports medicine instant cold packs that has a chemical reaction inside them that gets very cold very quickly. This is an endothermic reaction. So when we think about heat transfer, which is very much a part of combustion, we need to remember that what's going on is within the way physics works now, thermal equilibrium is always trying to be sought. So if there's something that's warmer next to something that's colder, the general motion will be that the warmer temperature will move towards the colder temperature until these reach equilibrium. If you think here of a rod that's been superheated on one end and is room temperature on the other end, what's going to happen then in conduction with this thermal transfer is the kinetic energy from the rapidly moving molecules and atoms down here on the hot end running into the colder ones, transferring their heat and energy that way. And so the heat moves down from the hot end towards the cold end, eventually reaching a place of equilibrium where this loses its heat, this gains the heat, and then they match. So heat transfer is very much a part of combustion. Conduction being one of those things, direct molecular transfer of heat until thermal equilibrium is reached. Another form of heat transfer is radiation. This is electromagnetic wave transfer of heat. Here we need to think in terms of the sun, which gives off electromagnetic waves or radiates radiation, and it heats the earth. It communicates it through the medium of a vacuum, space, but it still arrives here in the form of heat transfer, radiation, as it warms the earth and strikes the earth. So that would be a form of heat transfer radiation. And then convection. Convection is heat transfer through a fluid medium. Now when we say fluid, we don't automatically mean liquids. Fluids are also gases. So a fluid medium is a gas or a liquid. So you can get convection currents in air as well as in water. What you have then is heat is applied to the fluid, either gas or air, and as the fluid is heated, it gets less dense and warmer, and so it rises, causing the more dense, colder fluid then to move downward, and you get a circular motion. If we think in terms of boiling water, you can actually watch as it seems to churn up from the bottom. The heat source is there. The hot water becomes less dense, lighter, comes to the surface. The cold water sinks down, is heated, and comes up again. You can think in terms of air as well. Hot air, less dense, lighter, rises, cold air, more dense, heavier, sinks, is heated, and sent around. So you get these circular convection currents. So these are the main things to keep in mind around heat transfer: conduction, direct molecular, radiation, waves, convection, this circular motion through a fluid medium, gas or liquid. We talked about spontaneous combustion in your compost pile under auto ignition temperature, and then we've got hypergolic reactions here, or combustion. Basically that's a substance when brought into contact with another substance that immediately ignites without an ignition source necessary. It's just that type of reaction, and this is what they do in rocket engines. They have two separate substances kept in different compartments, and then they are injected into a third compartment at the same time. And when they meet and react, you get combustion automatically without an ignition source, which then they use to propel the rocket upwards. So hypergolic substances are those that ignite or combust when brought into connection with an oxidizer. So this substance brought into an oxidizer immediately combusts, and of course you get rocket explosions directed beneath the rocket, which sends it up. So hypergolic combustion. Well, this has just been a brief overview then of things related to combustion, some of the concepts, some of the vocabulary in those concepts. If you'd like to learn more about this and related matters, if you'll look underneath this video, there's a link down there. And if you'll click on that link, it'll take you to the website that has that information. And while you're on that website, you'll also find a link to an ebook that's ready for immediate download.
Enthalpy is the total thermal energy content of a system. So the total thermal energy content is heat plus work. Now, enthalpy is what we call a state function. Because enthalpy is a state function, we cannot measure it directly. We can only measure a change in enthalpy. And so a change in enthalpy is abbreviated by that symbol right there. Now, during any chemical reaction, there is a change in the enthalpy. So the enthalpy of the products is different from the enthalpy of the reactants. So a way to measure the change in enthalpy is by this equation right here. Change in enthalpy equals enthalpy of products minus enthalpy of reactants. Now, because most chemical reactions occur at constant pressure and volume, the change in enthalpy is equal to the heat released or absorbed. So we can set change in enthalpy equal to heat released or absorbed. And we can measure the heat that's being released or absorbed, so we can measure the heat flow by change in temperature, which is this symbol right here. Now, change in enthalpy is negative for exothermic reactions. So in exothermic reactions, the enthalpy of products is smaller than the enthalpy of reactants. And so you can easily just determine that by looking at this equation. When the reactants are bigger, it's going to create a change in enthalpy that is negative. And in an exothermic reaction, heat energy is being released, and so the temperature is going to rise. And so that's why the change in enthalpy is negative, because energy or heat is being released. Now, as you can probably guess, change in enthalpy is positive for endothermic reactions. And so here, that's when the enthalpy of the products is larger than the enthalpy of the reactants, creating a positive change in enthalpy. And so for an endothermic reaction, heat energy is being absorbed. And so the overall temperature is getting lower. But that's why change in enthalpy is positive, because enthalpy is being absorbed basically. The potential energy is constantly rising because energy is being absorbed. So that's a quick look at how enthalpy is the total thermal energy content of a system. Hess's law states that the enthalpy change for an overall reaction can be calculated by adding the enthalpies for individual steps in the reaction. So here we have a reaction of X changing to Y and then Y changing to Z. So based on Hess's law, this is an overall reaction. But we can find the total enthalpy change for this overall reaction by adding the enthalpies for the individual steps. So here's, we're trying to find the change in enthalpy for the overall reaction, and then we have the change in enthalpy for the individual steps. X changing to Y and Y changing to Z. So by adding those together, we get the enthalpy change for the overall reaction. Now, Hess's law can be used for enthalpy changes for reactions that are either too slow or too difficult to measure in a laboratory. Hess's law can also be used for the enthalpy change for an individual step reaction where you know the enthalpy changes of the overall reaction and the other step reactions. So I have an example of the use of Hess's law right here. In glycolysis, the series of chemical reactions that breaks down glucose in your body, glucose gets converted to fructose 1 and 6-biphosphate in 3 steps. And so I have those 3 steps right here. So with each step, we have reactants and then we have the products. And then I've written over here the change in enthalpy for each step. So all we have to do is just follow this up here to find the overall enthalpy. We just need to add these 3 changes in enthalpies of each step together. So we add negative 16.7 plus positive 1.7 plus negative 14.2. So when we've added all those together, I'll save you the math, we get negative 29.2, and then we just use the units that we've been using already, kilojoules over moles. So that's a practical example, a practical application of Hess's law. So remember that Hess's law says that the enthalpy change for an overall reaction can be calculated by adding the enthalpies for individual steps in that reaction. Most noble gases do not react with other elements. And so when we talk about noble gases, these come from the 6 elements in group 18, which is in the 18th column of the periodic table all the way to the right. And so these noble gases don't react with other elements, mainly because they have a full octet of valence electrons. And so these noble gases already have 8 valence electrons, so they don't need to engage in chemical reactions to gain more valence electrons, so they don't have a need to. However, under some extreme conditions, some noble gases can be made to react chemically. Now, xenon, which is a larger, heavier noble gas, is more likely to enter into a chemical reaction because its ionization energy is going to be lower than those of lighter, smaller noble gases like neon. And so an ionization energy is the amount of energy that it takes to remove an electron from an atom or molecule. And so xenon has a relatively low ionization energy, so it's not going to take a lot of energy for a reaction with it to take place. And so, like I said, the larger, heavier noble gases are the best candidates for engaging in chemical reactions. Now, xenon can react with fluorine to produce xenon fluorides. So that's one example of noble gas compounds. And then xenon can also, or xenon fluorides rather, can react with water, and they can produce oxygen-containing xenon oxyfluorides. So they can produce xenon oxyfluorides as well as xenon oxides. So that's a look at the reasons noble gases do not react with other elements and how it occurs when they do react with other elements. Absolute zero is the temperature of 0 degrees Kelvin. But I first want to look at how we get to that temperature. All right, so kinetic energy of gas molecules causes motion and is measured by temperature. And when gases cool, the kinetic energy of the gas molecules decrease, hence the temperature decreases. So let's go back up here. All right, so the kinetic energy of gas molecules causes motion. So it's the kinetic energy that makes things move, and this is measured by temperature. So it's not the temperature of something that causes something else. It's when gas molecules are in motion, we measure that amount of motion by temperature. Now, think about gases cooling. Now, don't think about it in terms of temperature. Don't think about it in terms of degrees. Just think about gases cooling. They're losing heat. So when gases cool, the kinetic energy of the gas molecules decreases as well. Now, what did we just learn about the kinetic energy of gas molecules? They cause motion. So if the kinetic energy of the gas molecules are decreasing, then the motion is decreasing as well. And then because of that, temperature decreases because the motion is measured by temperature. So if you think about molecules moving around and you can decrease the amount of motion they have, well, eventually, doesn't it make sense that at some point the molecules wouldn't be moving at all? Well, if the amount of motion of molecules is measured by temperature and the molecules aren't moving at all, then what would the temperature be? It would be 0 degrees. So that's how we get to absolute zero. Absolute zero is when the kinetic energy of a molecule is 0. And because the kinetic energy is 0, then molecular motion stops. And we measure molecular motion in temperature. So when molecular motion stops, we measure it in absolute zero, which is equal to 0 degrees Kelvin, K stands for Kelvin, or negative 273 degrees Celsius. Now, I didn't use Fahrenheit here because in science, we don't use Fahrenheit very often because that's not as important. So here we just have it in Kelvin or in Celsius. So 0 degrees Kelvin or negative 273 degrees Celsius is absolute zero. And that's when kinetic energy of the molecules is 0, and therefore molecular motion stops. Now, nothing can be colder than absolute zero because temperature is a measure of motion. And all motion ceases at absolute zero. So because the motion has all ceased and stopped, the motion can't stop anymore. So that's why absolute zero is absolute, because you cannot get any colder than that. Crystals of the same substance can have many different forms called allotropes. For example, carbon has many different allotropes. So these three substances right here are all made up of carbon, just in different forms, or allotropes. So the first is diamonds, and this is when atoms are covalently bonded to 4 atoms. So you have this one carbon atom that's covalently bonded to 4 neighboring carbon atoms, and that makes diamonds. And that makes a very rigid and hard structure, which is actually the hardest substance on Earth. Then there's also graphite, which is what pencil lead is made out of. And this is when the atoms arrange in hexagons and sheets. So these atoms are arranged in hexagons, and these hexagons are arranged in sheets that can slide back and forth on each other. And this makes something that's very soft, and so that's why it's used for graphite. And then there's this newly discovered substance that is made up of 60 atoms. Arranged in a hollow sphere, almost like a soccer ball. So these are all made up of carbon atoms. I didn't write it in all the descriptions here, but that's the atoms we're dealing with here. These are carbon atoms that are covalently bonded to 4 neighboring carbon atoms. Graphite is when carbon atoms are arranged in hexagons that are arranged in sheets, and this new substance is 60 carbon atoms arranged in a hollow sphere. So this is all made up of carbon, but we have 3 different substances. And that's because of allotropes, and that's when crystals of the same substance can have different forms. Dalton's law of partial pressures shows how to find the total pressure of a gas that is a mixture. Basically, we can say Dalton's law of partial pressures shows that individual gases in the mixture behave independently of the mixture, and they contribute to the pressure. So the equation we use for Dalton's law is P total equals partial pressure of gas 1 partial pressure of gas 2 and partial pressure of gas 3. So here we have the total. This is a mixture of gas right here. So we're looking for the total pressure. Then P1, P2, and P3 represent the gases that are making up this mixture. And this could go on and on. You get a P4, P5, P98, however many gases are in this mixture. And now we call these partial pressures. Well, when we say partial pressure, we're talking about the total pressure of this gas right here, gas number 3. The reason we call it a partial pressure is because it's only a part of the total pressure. So basically this total pressure is made up of 3 total pressures here. So let's look at an example problem. PO equals 122 kPa, so this is the partial pressure of oxygen. And notice here we're not using numbers anymore because we know the names of the actual gases. So the partial pressure of helium is 380 kPa, and the partial pressure of argon is 96 kPa. So now we can just plug that into the equation. P total equals P1 plus T2 plus P3. So notice here, since we know the pressures of all the gases, we're just looking for the total pressure now. So we just plug this in. 122 kPa plus 380 kPa plus 96 kPa. And I'll save you the math on that, but this is really simple. We don't even have to do algebra. We're just adding all these numbers together to get 598 kPa. Now let's look at this other example. All right, so the total pressure is 101 5/10 kPa. The pressure of oxygen is 21 3/10 kPa, and the other pressure we have here equals just 1 kPa. So the unknown is the pressure of nitrogen. So this is different than before. So let's go ahead and copy the equation. And we only have 3 pressures here, and that can be more or less, but we're just dealing with 3 partial pressures. Now, over here, we were trying to find the PTOT. That's what we're looking for. Now here, the P total. But notice here we already have the P total. So we're going to go ahead and plug that in there. Actually, let's not plug it in. Sometimes you can go ahead and plug the numbers in and then rearrange the equation. But sometimes it's easier if we go ahead and rearrange it. All right, let's get back here. All right, PTOT. So that's going to be on one side of the equation. So we'll just call Pn P3. In fact, I'll just replace it right now, Pn. So since these are all being added, we can just subtract P1 plus P2, just using a subtraction sign. So now the equation is going to look like this. So in other words, the partial pressure of nitrogen equals total pressure minus P1 plus P2, which really makes perfect sense because if the total pressure equals P1 plus P2 plus P3, and we're looking for P3, we're just subtracting the 2 other pressures from the total pressure. And so the remaining pressure must be the pressure of nitrogen. So now we just plug our numbers in, 101 5/10 kPa minus 21.3 kPa plus 1 kPa. So we just add these, 22.3 kPa, 101.5 kPa. We subtract there, and I'll save you the math. We get 79 2/10 kPa. And kPa is just short for kilopascals, which is a unit of pressure. So the important thing to remember about Dalton's law is it shows that individual gases in a mixture behave independently of the mixture, and they contribute to the pressure. So notice here we don't have to find the partial pressure of gas number 2 in light of the other pressures. All we're doing is we're finding the pressure of each gas and then adding them together to find the total pressure. And this equation can also be used, if we already know the total pressure, to find the partial pressure of one of the gases, like we did in this last example. We can define energy as the capacity to do work. And we could further define energy as a scalar quantity. And so when I say it's a scalar quantity, that means it's kind of like mass. It has a particular number and unit associated with it, but it doesn't matter in which direction the energy was applied. Now, a unit for energy is the joule, which is actually has a little j, but then when we abbreviate it has a capital J. So to give you an idea of the unit joule, 1 joule is the amount of energy used to apply a force of 1 Newton over a distance of 1 meter. So notice here that it applies both force and distance to come up with one single unit. Now you may be thinking, I said this was a scalar quantity, so direction didn't matter. Well, that's true, because say you're pushing a box and you give it 1 Newton of force, it does matter how far you pushed it, but it doesn't matter whether you push that box north, south, east, or west. So that's what we mean when we say it's a scalar quantity. It matters how hard you pushed it, but it doesn't matter in which direction you pushed it. Now, some other units for energy are watts, calories. There's several British thermal units that for energy. Kilowatt hours, which is used specifically for electricity. Now, energy and work represent a force acting over a distance. So I'm going to say that again. It represents a force acting over a distance. And so when we think about work, we may think about just doing some type of physical activity or going to the place of work. Well, we have a physics definition for work, and that means to move something over a certain distance. And so if I pushed on this wall and I pushed really hard, I pushed all day, but the wall never moved, I didn't do any work by the physics definition. Now, if I were to look at a big box on the ground and think, I want to move it across this parking lot, so I just push and push on it and slide it across the ground. Now I'm doing work because I'm moving that box. You have to move something. And so remember I said energy, or the unit we use for energy, which is a joule, is 1 Newton over a distance of 1 meter. So we notice here that distance is important. Because if I apply a force of 1 Newton on the box for 1 meter, I did quite a bit of work. But if I apply 1 Newton of force over a distance of 2 meters, I'm doing even more work because I'm pushing it even further. And so I used more work. And so energy is the capacity to do work. It's the ability to do work. It's just like if you get a good night's rest and you eat a lot of food, then you're going to have more energy to be able to do work than if you haven't eaten anything in a while and if you're pretty sleep deprived. So you have this more energy, you have more ability to do this work. And so if I push the box with a force of 1 Newton over a distance of 2 meters, I use more energy than if I push the box with a force of 1 Newton for only a distance of 1 meter. So you can see here the relationship between energy and work. Now I'm going to draw a little bit of a box right here to talk about the relationship between energy and mass. And so we have an equation, which is E equals m with a little o c squared. So E is obviously energy. And then we have m, which is mass. But in this case, notice it has a little o, which stands for the mass of the object. And then finally we have c squared, which is the speed of light in a vacuum. The speed of light in a vacuum. So that's the way that you can relate energy to mass. So you're looking at the mass of a particular object, and then you use the speed of light in a vacuum, which is going to be a constant, and you're able to relate these two variables back and forth to each other. So again, energy is the capacity to do work. The ideal gas law is P times V equals N times R times T. P stands for pressure, V stands for volume, N stands for number of moles, in other words, the amount. Moles is used to measure chemical substances. T is the absolute temperature, always in Kelvin, and R is the universal gas constant. And R takes different forms depending on the units that are needed. So R can look like this, or R can look like this. And notice the only difference here is the unit for pressure. Here, kilopascals are used, and here, atmospheres are used. So I want to go through an example problem so that we can better understand the practical application of this gas law. So the example problem we have is you have 30.0 liters of nitrogen gas at 373 Kelvin and 203 kilopascals. How many moles of nitrogen gas do you have? All right, so we're looking for moles here, and remember moles is in. So I'm going to put in question mark because that's what we're looking for here. All right, so let's go ahead and write the equation. PV equals nRT. All right, so we're looking for pressure, and we know that pressure is expressed in those units. So pressure is 203 kPa times volume, which is 30.0 liters. Now we're looking for moles, so we don't know what that is yet, so we'll just leave N there. Then we're looking for R, all right? And so we need to know which one to use, and the only difference here is the units. And so since we see kilopascals right here, that means we must be looking for that constant right there. So we have 8.31 finally times temperature 373 Kelvin. So from here, we just need to divide by this right here. And because we're using algebra here, what we do to one side of the equation, we also have to do to the other. So we'll divide this side by the same thing. All right, so all this right here crosses out because we're dividing one thing by the same thing. So the only thing left here is N, which is what we're looking for. So I'll save you having to go through all the math here, but what you would do is just multiply these two numbers and then divide it by these two numbers that are multiplied by each other. And so N equals 1.96. Now we need to know what unit to use. So in this case we're using moles, so I'll just abbreviate it MOL. And so that's the answer we were looking for. Now if you're wondering exactly how we got the units, well, everything has to cross out for something like this to work. So we see kilopascals here and there, so that can cross out. We see liters here and here, so that can cross out. And then right here we have moles in Kelvin times 373 Kelvin. So those right there cross out, because if you look at it like this, kPa is over moles K, and then we're multiplying it like this. So actually we don't need that number. So if we're just looking at units now. So this is what the units actually look like. Right, so that got crossed out from up there. We crossed that out like that, and then we're just left with moles. So that's where we got the unit here. So that's the answer right there. So that's the practical application. Because you have this equation now, if any of these are missing, any of these variables are missing, you can find the missing one as long as you have all the other information. Now obviously the missing information is never going to be this constant because you already know it. But if you're wondering what the pressure, the volume, the number of moles, or the temperature is, as long as you know the other three variables, you can figure out that missing variable. Ionic bonds tend to form under two certain criteria. And the first is ionic bonds tend to form between metals and nonmetals. So if you have two elements and one's a metal and one's a nonmetal, an ionic bond is likely to form. Now the second criteria is that ionic bonds tend to form between elements with a large difference in electronegativity. So the larger the difference in electronegativity, the better the chance ionic bonds are going to form. And so if elements meet both of these criteria, there's a very good chance they're very likely to form ionic bonds. Now, keep in mind that elements with the highest electronegativity values are in the upper right-hand corner of the periodic table of elements, while those with the lowest are near the lower left-hand corner. So you have elements with low electronegativity down here and elements with high electronegativity up here. And so just by knowing those two facts right there, if you see an element on the periodic table, if you just imagine this board as the periodic table, and it's about right here, you just know by where it's geographically situated on the board that there's a really good chance that it has a high electronegativity because it's near the top right-hand corner of the periodic table. Now, I have some pairs of elements here, and I want to examine these elements to see if they meet this criteria and determine whether or not they are likely to form ionic bonds. So first we have nitrogen and oxygen. Now, nitrogen is a nonmetal, and then oxygen is obviously a nonmetal. So they are not likely to form ionic bonds because there is not between a metal and a nonmetal. We have two nonmetals here. Then we have potassium and fluorine, and potassium is an alkali metal, and fluorine is a nonmetal. So we've met the first criteria. We have reaction here between a metal and a nonmetal. So we're doing good so far. And then there's a high electronegativity difference here, and it's actually 3.2, which is pretty high. So they're likely to form ionic bonds, specifically potassium chloride. Now here we have barium and sulfur, and barium is a metal, and then sulfur is a nonmetal. So here we have a metal, a nonmetal. We're doing good so far, so they're likely to form ionic bonds, specifically barium sulfide. And then in addition to that, their electronegativity difference is moderately large at about 1.6. Now finally, we have cesium and tin. And cesium is an alkali metal. And then I'm sure you can guess that tin is a metal. So here we have two metals interacting with each other, so it's not between a metal and a nonmetal. So these cesium and tin is not likely to form ionic bonds. So notice here the main factor here was that we had two nonmetals and two metals here. But when we have a metal and a nonmetal, they're likely to form ionic bonds, and especially if they have a high electronegativity difference. So hopefully through this short session, you have a better understanding of ionic bonds. The strength of the ionic bond contributes to the property of hardness and brittleness in ionic compounds. Now, you may be thinking, okay, how can something have the property of hardness and brittleness? Well, it can. And in this case, ionic compounds are both hard, but they also can be very brittle. And so there's a strong ionic bond between anions and cations. And this strong ionic bond causes the ions to be close together in tightly packed crystal lattices. And because they're close together, you have positive ions up next to negative ions. Now, when a force is applied to the crystal deforms slightly. So I'm going to draw an arrow right here that represents force. And so now the crystal deforms slightly. And this deformation brings the positive ions next to positive ions and negative ions next to negative ions. So now this is rearranged a little bit, and you have positive, 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 negative, 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 negative. And so now this is where the problem comes in. And the positive ions repel the positive ions, and the negative ions repel the negative ions. So now positive and positive want to get away from each other, and negative want to get away from each other. And the repulsive forces between the similarly charged ions are so great that the crystal ends up shattering. And so that's how ionic compounds can be both hard and brittle. They're hard, but they're also brittle because they can break under much force. And so the break is usually along defined planes within the crystal. ionization energy is the amount of energy that it takes to remove the first valence electron of an atom. So basically, ionization energy is a measure of how easy an atom loses its valence electrons. Atoms like sodium and potassium, which give up valence electrons to form ions, would have a low ionization energy because they give up their valence electrons easily. So if you think about the periodic table like a rectangle, even though it's not a perfect rectangle, you have rows, or we can also call them periods, that run from left to right. Now, as you go from left to right, the ionization energy increases. So the farther you go to the right down a row, the larger the ionization energy gets. So fluorine has a higher ionization energy than does lithium because fluorine is farther to the right than lithium. Now, as you go up the periodic table, up a column, or we can also call them groups, as you go up, the ionization energy also increases. Now, there's a reason for this. This is because of the shielding effect of inner electrons. For example, compared to lithium, lithium has fewer inner electrons between its nucleus and outer shell. Therefore, lithium has a higher ionization energy than cesium. So an element that's over in this region is going to have a much higher ionization energy than one that's over here, because this one's to the right and farther up in the periodic table. This one's lower and farther to the left. So just by knowing the two facts that ionization energy increases to the right and as you go farther up the periodic table, you can just look at an element, look at where it's geographically situated on the periodic table, and get an idea of how high its ionization energy is when compared to other electrons. So the important thing to pull out of this session is that ionization energy is the amount of energy that it takes to remove the first valence electron of an atom. The elements iron, cobalt, and nickel are three interesting elements. So they're in the groupings, or they're in the groups 8, 9, and 10. So they're in different groups, but they all are in the same period or row. Period 4. So here you have iron, cobalt, and nickel. And they have different atomic numbers as well. These numbers, like I said, are in the same period, have the same number of valence electrons. They all have 2 valence electrons, but they're in different groups. And so they are in a section of the periodic table called the D block elements. In this section, as the atomic number of electrons increases after the s orbital is filled, the electrons are filling the d orbitals from the previous energy level. So basically, once the 4s orbital is full, 3d filling occurs. And so the way this process works, the 3D won't start filling until the 4s orbital is full. So what that means is the 4s orbital, or let me say it this way, there's going to be an equal number of valence electrons. And that makes sense because the 4s orbital is always going to be filled up, so there's always going to be equal number there. But the difference is how much the 3D is filled. And so that results in an unequal number of 3D electrons. So again, iron, cobalt, and nickel are in what we call the D block of the periodic table of elements. And so they're in the same row, but different columns. And so the 3D does not start filling until the 4s orbital is full. This causes there to be an equal number of valence electrons above them, but an unequal number of 3D electrons. The 3 laws of thermodynamics are important to our understanding of energy and heat. So I've written each law up here on the board, and then under each law, written a brief summary of that law. So the first law of thermodynamics says that energy is always conserved. So take, for example, when I rub my two hands together. So I'm rubbing my hands together. So I'm exerting energy to rub my hands together. So it would look like my body is losing energy because I'm having to exert that energy to rub my hands together. But because I'm rubbing my hands together, I'm creating friction, which creates heat, and I can feel my hands getting warm right now. So although energy is coming out of my body to rub my hands together, it's changing forms into the form of heat. So heat is another form of energy. So energy is always conserved. It may change forms, but the energy is always there. You can't destroy energy. The second law of thermodynamics is that a system will develop a uniform temperature. So say I had a box, and inside that box I had 2 blocks of metal, and the blocks of metal were of equal weight. The first block of metal weighs 100 degrees, and the second block of metal weighs, the first block of metal is 100 degrees, and the second block of metal is 0 degrees. So eventually those 2 blocks are going to balance each other out until both blocks weigh 50 degrees. So that's basically the second law of thermodynamics, that both blocks in the box are going to work together to find one temperature, an equilibrium, a temperature that each block is going to have. So this can be applied to many different things, any sort of system that you have where you have different objects inside that system and they have different temperatures. Eventually all the objects in that system are going to have the same temperature. The third law of thermodynamics is that entropy becomes constant as temperature approaches 0. Now this doesn't really make sense unless you know what entropy is. Entropy is the flow of heat. So as the temperature approaches 0, the flow of heat becomes constant. So that's a look at the 3 laws of thermodynamics and how they affect our world. When a substance melts, the atoms, ions, or molecules that make it up begin to become loosely associated. Now, in order to make the atoms, the ions, or the molecules loosely associated, it takes energy. And so it's energy that's used to make them loosely associated. So you need lots of energy. Now, ionic compounds have high bond energies. So because of, if anything's an ionic compound, it's going to take a high bond energy to break it up, to loosen everything up. And if you're not familiar with the bond energy, basically that's the amount of energy it takes to break something up into its original parts. So basically it's the amount of energy that it takes to break an ionic compound up. Now, aluminum oxide is an ionic compound of aluminum and oxygen. So remember, I said it's an ionic compound, so that means it must have a high bond energy. And so it's going to have a higher bond energy than its original parts. And so the melting point for aluminum is 660 degrees Celsius. But since we have an ionic compound here of aluminum oxide, you know the melting point is going to have to be it's going to have to be even higher because the ionic bond between aluminum ions and oxygen ions is very strong. So the melting point of aluminum oxide is a lot higher. Like I said, it's actually going to be 2054 degrees Celsius. So you can see here how much of a difference in the melting point ionic compounds make. So the important thing to remember is that when a substance melts, the atoms, ions, or molecules that make it up become loosely associated. In metal cations are surrounded by a sea of valence electrons. And these valence electrons are said to be delocalized. So I'm going to write that up here on the board because that's an important point. And what delocalized means is that these valence electrons aren't attached to a single atom. Instead, they float around many atoms. However, the non-valence electrons are still associated with individual atoms in the metal. All right, so in addition to being delocalized, valence electrons are attracted to metal cations, and that's what creates the metallic bond. So I'm going to write up here on the board, attracted to metal cations. So I hope you're tracking with me. Remember, valence electrons are delocalized. They're attracted to metal cations, creating metallic bonds. Now, because these valence electrons are not held tightly in the metals, they have different properties from other ionic solids. So this means they are malleable, which means they're able to bend. They are also ductile. They can be drawn into wire. So in addition to being malleable and ductile, metals have varying melting points from low to high. And the sea of electrons moves freely and conducts electricity, so metals are good conductors. So I'm going to write good conductors. We also said they have variable melting points. So the important thing to remember is that metal cations are surrounded by a sea of valence electrons that aren't attached to any one atom, but just float around. And they're attracted to the metal cations, forming metallic bonds. And because these valence electrons are not held tightly in metals, they have different properties from ionic solids. A molecule is an electrically neutral combination of two or more atoms of the same or different elements joined by covalent bonds. So I want to go ahead and break down this definition a little bit to make sure we really understand it. Notice up here it says that the molecule is electrically neutral. So that means it has no net charge. So any positive or negative charges in that molecule cancel each other out, so there's no net charge. In other words, it's neutral. Now, it's a combination of two or more atoms. Now, so this could look like this. Two hydrogen atoms or one oxygen atom and one hydrogen atom together would work as well because they have to be of the same or different element. So either one of these works as a molecule. Now, these are some really simple examples of molecules. And so molecules can be simple like those right there, or they can be as complex as large biochemical macromolecules such as proteins, starches, and cellulose. Now, proteins can range in size from 50 to more than 2,000 amino acids linked by peptide bonds, while starches and cellulose molecules can consist of more than 10,000 smaller glucose molecules covalently linked together. Now, there are some substances out there, three in particular that I want to highlight, that you may think are molecules which actually are not classified as molecules. So I want to go over those. So one is aggregations of polar molecules joined temporarily by hydrogen bonds. Another example is electrically charged ions joined by ionic bonds. And then finally, metals consisting of positively charged ions in a sea of delocalized electrons. So these three substances that I just listed, you may be inclined to classify these as molecules, but they actually are not. So I just wanted to warn you about those. So let's just review the definition for molecules again. That's something that's electrically neutral of two or more atoms of the same or different elements, and they're joined together by covalent bonds. So remember all these things. They're neutral. There has to be two, but there can also be more. Same elements or different elements. And they have to be joined by covalent bonds. So generally, when you have a definition of something, it just usually is maybe twofold. Here, there's lots of different criteria something has to meet in order to be a molecule. So you want to be able to remember all these so that you can see a substance, learn a little bit about it, and be able to identify if it is indeed a molecule. Nuclear charge is influenced, or mainly influenced, by the number of protons. Now, we're also going to take a look at effective nuclear charge, which is influenced by the nuclear charge and the number of electrons that shield the nucleus from the outer shell. So let's go ahead and look at the nuclear charge in relation to the periodic table of elements. as you move to the right of the periodic table, nuclear charge is going to increase. And as you move down the periodic table, the nuclear charge is also going to increase. So when you get towards the bottom right corner of the periodic table, the nuclear charge is going to be very strong. If you're at the top left, the nuclear charge is going to be pretty small. Now, the effective nuclear charge, like we said, first takes into account the nuclear charge. And so as you move to the right, the effective nuclear charge is still going to increase, because as you move to the right of a period or a row, the nuclear charge is increasing, but the shielding is staying constant. So overall, the nuclear charge is increasing. Now, when you go down a column or down a group of the periodic table, the effective nuclear charge is decreasing, or it decreases. So now you may be thinking, okay, how can this work? Because the nuclear charge is increasing as you move down the periodic table. So why isn't the effective nuclear charge increasing as well? That's because although the nuclear charge increases down a group, the shielding also increases. And the farther you go down, the more the shielding effect outweighs the increase in nuclear charge. So eventually, the shielding effect is going to outweigh the increase in nuclear charge, so the effective nuclear charge is actually decreasing as you move down a group or column of the periodic table. And then one last note that I forgot to mention on the nuclear charges: as the atomic number increases, the nuclear charge increases. That's generally how it works. And so you can see that as the atomic number increases, the nuclear charge is also increasing. But just by remembering these few facts about whether the nuclear charge or effective nuclear charge increases or decreases as you move around the periodic table can help you just look at an element, see where it's geographically situated on the periodic table of elements, and get an idea of how strong its nuclear charge is. The periodic table is a way to systematically display the chemical elements. Now notice I said that it consists of chemical elements, and it consists of elements only. So this does not include mixtures and compounds, because an element is basically matter in its most basic form. The periodic table positions chemical elements based upon atomic number. An atomic number is the amount of protons an atom has in its nucleus. So hydrogen is the first element on the periodic table because it has one proton in its nucleus. And then the next chemical element has more protons in its nucleus. Like I said, the periodic table arranges chemical elements very systematically. So if you were to take a look at one row on the periodic table, all the chemical elements on that one row would have the same number of electron shells. And if you were to take a look at one column, all the chemical elements in that column would have the same electron configuration. So the periodic table arranges the elements in such a way that all the elements are next to similar elements. So if a scientist knew a lot about one element, he could know a lot about the elements around it just because all the elements are grouped together with similar elements. There are about 118 elements out there, but only 114 have been officially recognized. And 98 of those are natural elements, ones that naturally occur in nature, such as potassium, nickel, and hydrogen. The other ones are synthetically produced by humans, such as Einsteinium. So the important thing to remember about the periodic table is that it consists of chemical elements and it is arranged by atomic number. Reduction is when the atoms or ions of an element become more negative or less positive than they were before. So in other words, when an atom or ion undergoes a change in oxidation state in the negative direction, it is reduced. So take a look at this reaction right here between sodium and chlorine. Here, the chlorine becomes a chloride ion because it's becoming negative here. And that's why it has the negative symbol right here. Now, the element chlorine has an oxidation state of 0. And that's because all elements in their natural state have oxidation numbers equal to 0. Now, the chloride ion has an oxidation state of -1. So the net change of oxidation for chlorine is in the negative direction. So by definition, chlorine is reduced here. Now, whenever an atom in a reaction gets reduced, some other atom gets oxidized. That's because what determines reduction is how many electrons something has, or if the atom is gaining electrons. So when an atom gains electrons, then that means some other atom had to give up electrons. Those electrons didn't come out of nowhere, so another atom had to give up electrons, becoming less negative. And so that's oxidation. Oxidation is the opposite of reduction. So there's a balance here. When one atom gains electrons, another one loses it. But the atom that gains electrons is considered to be reduced. I want to take a look at the properties of solutions and some different types of solutions. But first off, we need to define what a solution is. And it's a homogeneous mixture of two or more substances in a single phase. So by homogeneous, we mean the same. In other words, you don't have two substances somewhat mixed together. They are completely mixed together, forming one substance or one solution. And they're in a single phase. In other words, they're either all the components of the mixture are either in liquid, solid, or gas form. They're not in different forms. So every substance in the mixture is combined together to be the same in the same phase. And in the case of a solution, the particles are distributed uniformly throughout the volume, and the molecules do not react chemically with each other. So in any solution, you have two parts, the solvent and the solute. Now, like we said, a solution can be made up of two or more substances, but here we're just going to pretend that there's two substances. So we have the solvent and the solute. We have one solvent and one solute. So consider water and sugar. So the solvent here would be water, and the solute would be sugar. So the solvent is what is dissolving something, and the solute is what is being dissolved. So if you were to put sugar inside water, water would be the solvent because it would dissolve the sugar, and the sugar would be the solute because it's being dissolved. Now, like I said earlier, when you put sugar into water, the sugar is not going to stay in there. You may go to the bottom at first, but if you stir it around, eventually the water is going to break down those sugar, the little pieces of sugar, until the sugar is completely dissolved, and the sugar is going to be distributed uniformly throughout the volume. If you were to take a teaspoon of that water, there'd be a certain amount of sugar in that water. And if you were to take another teaspoon out of that water, there'd be the same amount of sugar in that section of the water because the particles are distributed uniformly throughout the volume. And now notice that the water was in liquid form and the sugar was in solid form. But notice that they're in a single phase now. The sugar has become liquid form. And then we said they form a homogeneous mixture. There's not some pieces of sugar and some water. The sugar has now been completely dissolved in the water, so now you just have sugar water as a whole. And then also, the water and sugar are not reacting chemically with each other. Now, there are three different kinds of solutions: gaseous solutions, liquid solutions, and solid solutions. And now, the name associated with each kind of solutions describes the phase of the solvent. So in the case of a gaseous solution, the solvent is in the gas phase. And in a liquid solution, the solvent is in the liquid phase. And then, I'm sure you're getting the picture, in solid solutions, the solvent is in the solid phase. And then the solute can be in any phase. So that's just three ways to classify a certain type of solution. But the important thing to remember, if you just take one thing away from this session, is that a homogeneous mixture of two or more substances in a single phase is what we call a solution. The three classical states of matter are solids, liquids, and gases. So first we're going to look at solids, and we're going to look at some of the characteristics of a solid. So solids have a definite volume and density. So we would say they have a definite volume and density at a given temperature and pressure. So like this whiteboard, for example, is a solid. So the volume of this whiteboard isn't changing, and the density of this whiteboard isn't changing. And then the second point of a solid is it has a degree of structural rigidity and a constant shape. So notice that this whiteboard has structural rigidity and a constant shape, so the shape isn't changing. It also has a resistance to flow. Now, some solids, such as modeling clay, can flow and undergo deformation under pressure. So I'm just going to write here, there are exceptions, but for the most part, solids have a resistance to flow. Now, the second state of matter is the liquid. And like solids, at a particular temperature and pressure, it has a definite volume and density. So the reason I say at a certain temperature and pressure is because at a different temperature and a different pressure, this whiteboard may have a little bit of a different volume and a little bit of a different density. But as long as it stays at the same temperature and pressure, then it's going to stay the same. The volume and density are going to stay the same. The same thing with a liquid. Now, a liquid does flow readily, so that makes it a lot different than a solid. But it does not expand to fill a container. So it's going to flow readily. If you spilled water on the ground, it wouldn't all just stack up in one spot. It would flow all over the place. Well, if you were to pour water into a glass, the water isn't going to expand to fill up that whole glass. It's going to keep the same volume. Now that's different than the third state of matter, which is a gas, because the main thing about a gas is that it will expand to fill a container. So all of a sudden, if a gas was exposed in this room, it wouldn't all stay in one spot. It would eventually move to fill the entire room. Now the molecules are spread much farther apart, and they move more rapidly and randomly than in a liquid. So basically, the molecules move the slowest in a solid, they move a little faster in a liquid, and then they move the fastest in a gas. And so that's why gases are spread apart. It's because they're moving around so much and bumping into each other and pushing away from each other. And a liquid has more movability to it, I guess, if that's a word. It can move more because the molecules move more. And then a solid, you think about ice, it's not really doing anything. It's just sitting there because it's a solid. The molecules are moving really slowly. And so a gas is far more dispersed than even a liquid because it'll expand to fill an entire container. And so that's a look at the three states of matter. Elemental sulfur comes from deposits in the ground. Now, sulfur has two physical properties that are used in the extraction process, and those are low melting point and low density. Now, the extraction process is called the Frasch process, and there's basically 7 steps to how it works, but the steps aren't very complicated, so we're going to go ahead and dive right in. So starting out, a well is drilled into a sulfur mineral deposit. So after that well is drilled, superheated water is pumped into the deposit. And so this superheated water is usually heated to around 170 degrees Celsius, which is about 340 degrees Fahrenheit. So that water is pumped down into the deposit. And as a result of that, the hot water melts the sulfur in the deposit. Now remember earlier I talked about 2 physical properties of sulfur that are useful in the extraction process. And the first was its low melting point. So you've already seen that come into play. The low melting point of sulfur allows for the water to melt that sulfur. Now remember that although this is melted, the sulfur is still down in that deposit, but we're trying to extract that sulfur. So in addition to superheated water being pumped into the well, compressed air is going to be pumped down into the well. And so because of that compressed air, the molten sulfur comes to the surface because all that air is forcing it to the surface. Now remember earlier I talked about the 2 physical properties. Well, the second one was low density. So you've also seen that physical property come into play. the low density of sulfur allows compressed air to be able to push it to the surface. Now that the molten sulfur is at the surface, it can cool and solidify. And so from there, the sulfur forms a rhombic crystal. And so a rhombic crystal has 8 molecules. So those are the 7 steps to the extraction of sulfur in what we call the Frasch process. Titration is a technique to determine the concentration of an unknown solution. So this unknown solution is usually going to be an acid or a base. And so titration isn't the name of a chemical or anything. It's just this process we're using, or this technique, in order to determine the concentration of this unknown solution. So there are some solutions out there which we call a standard solution, which we know what that solution is. We know the chemical makeup of it. So we take known volumes of the standard solution and we add those to the unknown solution. Now, while the volumes of the standard solution are being added to the unknown solution, it's important to measure the pH of the solution, because eventually the standard solution is going to neutralize the unknown solution. Okay, so it's eventually going to neutralize that unknown solution. And when that happens, the pH of the unknown will change rapidly. And so we call this the endpoint of titration. So this is the endpoint of this technique we were using, because the standard solution neutralizes the unknown solution. And so at that point, the pH of the unknown is changing rapidly, so that signals the endpoint of titration. It signals that this process, this technique, is over. And so by knowing the amount of standard added to reach the endpoint, remember we said we're going to add known volumes. So because we know the amount of standard added to reach the endpoint, the moles of the unknown neutralized can be calculated. So the moles of the unknown neutralized and the volume of the unknown help us determine the concentration of the unknown. So if you had trouble following with me on that last part, I'll go through it again. So we know the amount of standard added to reach the endpoint. And so because of that, we can calculate the moles of the unknown neutralized. So then we take the moles of the unknown neutralized along with the volume of the unknown, and we can determine the concentration of the unknown. So that's how the titration technique is used to determine the concentration of an unknown solution. Stoichiometry examines the quantitative relationship between reactants and products in a chemical reaction. Now, stoichiometry applies Dalton's atomic theory and the laws of constant composition, multiple proportions, and conservation of mass. And it does that to quantify relationships between reactants and products as described in a chemical equation. Now, we can say stoichiometric calculations use information from the chemical equation to determine the amount of reactants that will produce an amount of products. So I want to take a look at how we use stoichiometry in real life. So first, we're going to find the conversion factor. And so we have this reaction right here, and we have mercury oxide here, and then we have an oxygen molecule over here. And notice the coefficient for mercury oxide is 2, and the coefficient over here is 1. So another way to say conversion factor would be to say conversion ratio. And so we have a ratio of 1/2 here of the oxygen molecule to mercury oxide. Now, we're now going to move into using the conversion factor. So we're going to take the conversion factor, and we're going to multiply it by the quantity of reactants. And we're doing this in order to find the quantity of products. So say we have 0.5 moles of mercury oxide. And we're going to take that and we're going to multiply it by the conversion ratio. So that's going to equal 0.25 moles of the oxygen molecule, which makes sense because we see by the ratio here that we have twice as much of mercury oxide as we do of the oxygen molecule. So if we have 0.5 moles of mercury oxide, then we're going to have half that amount when it comes to the oxygen molecule. Now, if we don't know the quantity of reactants, but we do know the quantity of products, we can use the quantity of products along with the reactions, or the conversion factor, to find the quantity of reactants. So we're going to take the quantity of products and we're going to divide that by the conversion factor. So the quantity of products here is 0.25 moles of the oxygen molecule over 1. Now we're dividing it by the ratio, so it's going to be 2 over 1 now. And we just need to be sure that we label everything, because now the oxygen molecules are going to have to cross out. 0.25 times 2 equals 0.5 moles of mercury oxide, which we know that's correct because we were told at the beginning of the problem that that's how many moles we had. So that's how you can use the quantity of products or the quantity of reactants along with the conversion factor to find whatever is missing. So remember that stoichiometry examines the quantitative relationship between components, such as reactants and products, in a chemical reaction.
Proteins. Proteins are large biological molecules consisting of one or more chains of amino acids, which are known as polypeptides. So a polypeptide is an amino acid chain, not just an amino acid, but the whole chain of them connected. Now, proteins have different structures based on how many of them are present. So the primary structure of a protein is its amino acid sequence. So just the one chain, the one polypeptide chain, and what sequence those amino acids are taking. The secondary structure is the regularly repeating local structures stabilized by hydrogen bonds. Now this is whenever we've got a few proteins interacting together and the local structures or the regular structures that these proteins will form just all on their own without any help. And some examples would be the alpha helix, beta sheet, and turns. So those are just some different shapes that the proteins can take whenever there are a few of them joining together with hydrogen bonds. Now the tertiary structure is getting more complex. It's the overall shape of a single protein molecule. So enough proteins have joined together to make a whole molecule, and the tertiary structure is referring to the spatial relationship of secondary structures to one another. So you've got your alpha helices, your beta sheets, and your turns, and it's how they interact together and what kind of shape they all form whenever they form into a single molecule. And you've got proteins joining together and then more proteins with hydrogen bonds joining together into a larger molecule, and what that molecule looks like spatially. The quaternary structure is going to be the structure formed by several protein molecules. So you can see how we just keep adding proteins here to get different structures. And the more that are added, the more different that these structures are going to look because they're getting more complex. So several protein molecules are joined together in the quaternary structure, and this is usually called a protein subunit. So it's no longer one molecule, it's multiple molecules. So it's a subunit which functions as a protein complex. So it's going to be more complex, it's going to be able to process more complex functions. And a lot of the time what you're going to see is the quaternary structure of a protein, because you have lots of them together and they are drawn toward each other and then they bond. Now let's look at some of the functions of proteins. We have structural proteins, and these give stiffness and rigidity to biological components that would otherwise be more fluid. They wouldn't have a lot of shape to them. An example is keratin. Keratin is a protein found in our hair, nails, in birds' feathers, and in animals' hooves, and it gives them a hardness that they wouldn't otherwise have. It's not a part of your body like your skin or an organ, and you can feel they're a lot harder than your skin would be. Like your nail and your hair don't feel the same as your skin feels or as your internal organs would feel, and that's because they have this protein present that gives them more rigidity. So structural proteins are going to make things stiffer and give them a harder shape. Next we have enzymes. And enzymes catalyze chemical reactions. So there's a chemical reaction that needs to take place, but it won't be able to take place until this enzyme is present. When the enzyme is present, it catalyzes the chemical reaction and speeds it up and lets it occur. Next, you've got receptors. Proteins that function as receptors bind a signaling molecule to induce a biochemical response. So it receives that signaling molecule and then it binds it somewhere that will induce the biochemical response that needs to happen. Next, you have antibodies, which are also known as immunoglobulins, and these bind antigens and target them for destruction. So an antigen is a foreign body that comes into the cell and it's not welcome, it's seen as the threat, and so these antibodies or immunoglobulins are part of the immune system, and they bind to the antigens or that foreign body and they target them for destruction so that then they are destroyed and removed from the cell and the threat is eliminated. We also have motor proteins. And motor proteins generate the forces responsible for muscle contraction. So think about your motor functions, being able to move your muscles, being able to move around. All of those are able to happen because of these proteins, these motor proteins. So if you're able to move your arm back and forth, if you're able to close and open your hand, those are responsible. Those are happening because of muscle contractions, and those muscle contractions are generated by motor proteins. If we didn't have those, we wouldn't be able to contract our muscles like we are. Next, we have pump proteins. So these are proteins that act as a kind of pump, and they transport ions or small molecules across a membrane. So you've got a cell membrane or an intercellular membrane, and the proteins can act as a pump and push these small ions or molecules across the membrane. And that is their primary function as a pump protein, is just to transport these small molecules or ions across the membrane. Lastly, we've got switch proteins, and these act as an on-off switch based on the presence or absence of certain other molecules in the cell. So if a cell was waiting for a certain molecule to be present to do something, then the switch protein is going to act as an off switch and keep the cell from performing that function until the certain molecule it's waiting on is present. Once it's present, it flips the switch and says, basically, it's on. It can perform this function now. So it acts as like an on-off switch for the cell. As you can see, proteins are very important in a cell. They actually can make up a large percentage of the components of a cell. For instance, you could have a cell that was made up of maybe 3% DNA, which is really important. You have to have the DNA encoded correctly for everything else in the cell to function. But the protein could make up almost 50% of that cell's components. So while it isn't maybe as biologically important as that DNA is, it makes up a big part of that cell, and not much would be going on if it didn't have protein there as well, because protein has a lot of functions. So you can see that proteins are very important for cell life and lots of cell functions.
pH is basically a measure of how many hydrogen ions are in a substance. pH is very important to many fields such as biology, chemistry, medicine, food science, farming, and water treatment. I've written up here on the board a pH scale ranging from numbers 0 to 14, each indicating the amount of pH in a substance. Now there are pHs that go higher than 14, but for practical purposes, this is the largest pH scale we need. Water has a pH of 7, and any substance with a pH larger than 7 is considered a base. So everything from 7 over to 14 is considered a base. Common bases that you probably know of are baking soda and bleach. Now any substance with a pH below 7 is considered an acid. Some of those that you may know of are lemon juice, tomato juice, and gastric acid. So water is kind of the middle bar on the pH scale, and anything to the right is the base, and anything to the left is an acid. We're going to take a look at strong acids and weak acids, as well as strong bases and weak bases. Now, strong acids and strong bases obviously have their differences because one's an acid and one's a base. But they do have two things in common, and that's that strong acids dissociate completely in water, 100%. And they are also strong electrolytes. Now, an example of a strong acid is hydrochloric acid, and an example of a strong base would be sodium hydroxide. Now, like strong acids and strong bases, weak acids and weak bases have their obvious differences, but they do have one thing in common, and that's that they do not dissociate completely in water. So just stick with me here so you can remember the differences, that strong acids and strong bases do dissociate completely in water, but weak acids and weak bases do not dissociate completely in water. An example of a weak acid is hydrogen sulfide, and an example of a weak base is ammonia. So that's a quick overview of strong and weak acids and strong and weak bases. Some common types of lipids that you are probably familiar with are fats, oils, and waxes. Now, like carbohydrates, lipids are organic molecules. However, lipids have a more complex structure than carbohydrates and are larger molecules. Now, lipids include several different types of groups, and so the first is triglycerides. And so, stated somewhat simply, triglycerides consist of a glycerol molecule that is bound to 3 long-chain fatty acids. So, glycerol is a polyalcohol, and fatty acids are long-chain carboxylic acids. So, triglycerides are the most common lipids and make up fats and oils. Now, a second grouping is phospholipids. And these consist of 2 fatty acids bound to a phosphate head group. And so the fatty acid portions avoid water, meaning they're hydrophobic, while the phosphate head groups seek water, meaning they're hydrophilic. So phospholipids have a structural function. They make up a cell and organelle membranes in your body. A third group is steroids, which are lipids that are derived from cholesterol. Steroids have a 4-ring structure with a hydroxyl group at one end and a short carbon chain at the opposite end. Cholesterol is also found in cell membranes and circulates in the blood. Another type of steroids are hormones. Now, the fourth group of lipids that we're going to talk about are waxes, which are formed when a long-chain alcohol binds to a long-chain fatty acid. So again, some common types of lipids are fats, oils, and waxes. And like cholesterol, lipids are organic molecules. Despite their similarities, RNA and DNA differ in terms of structure and function. For example, RNA has a different sugar than DNA. RNA's sugar is ribose. However, DNA's sugar is deoxyribose. When it comes to nitrogenous bases, they have 3 of the same bases. They both have adenine, guanine, and cytosine. However, uracil is only found in RNA, and thymine is found only in DNA. RNA only has 1 strand. However, DNA has 2 strands. In fact, if you were to straighten out DNA, it would have 2 side rails. And then finally, when it comes to the relationship between RNA and DNA, RNA aids in gene expression, replication, and transportation. So in spite of the 3 differences I just pointed out to you, they still have this relationship where RNA helps support the functions carried out by DNA. And out of these 3 differences, it could be said that the differences in sugar between RNA and DNA is their greatest difference.